Broadcast is now starting. All attendees are in listen-only mode.
Welcome to Optical Metrology Solutions for the Semiconductor and Microelectronic Industries, a webinar presented by Sensifar Metrology and hosted by Photonics Media. My name is Robin Riley, and I'm the Photonics Media web editor. I would like to introduce Adam Platisse, U.S. Sales Manager for Sensifar Metrology, and Alberto Aguirre, Vice President of Sales for Sensifar Metrology. Adam and Alberto will be speaking today on quality control analysis in PCB applications and Sensifar's proprietary technology for quality analysis and control of high-throughput environments. If you have any technical issues during the webinar, please log out and log back in to rejoin. A recording of the webinar will be available on the Photonics Media website shortly after the presentation. We encourage you to ask questions throughout this presentation. Just type your question in the question box to the right of your screen, and we will answer as many as possible at the close of the webinar. Before we begin, we'd like to briefly poll our attendees. I have 4 polls here, which I will try to get through quickly. So let me launch the first poll. And the question is, what is the most important feature or capability you require from an optical metrology system? The possible responses being speed, reliability, usability, or response time and support. I'll give you a few more seconds to respond. Okay, I'm going to close this and share your results. And 8% of you said speed, 65% said reliability, 25% of you said usability, and 2% said response time and support. So I'm going to hide this. Excuse me a minute there. Okay, for our next poll. Okay, the question is, which measurement technology are you currently using? The possible answers are none, stylus profiler, AFM, optical profilometer. I'll give you a few more seconds as we collect the response. Okay, I'm going to close that, share your responses. 40% said none, 6% said stylus profiler, 8% said AFM, and 47% said optical profilometer. And here's our third question. Third question, what is your main interest or application for using an optical profilometer? Your choices are research, quality assurance, or quality control. Give you a couple more seconds. Okay, I'm going to close that poll. Share the results. 61% said research, 9% said quality assurance, and 30% said quality control. Okay, for our final question. Okay, our last question here is, how soon are you looking to purchase a new optical profiler? The choices are immediately, 1 to 3 months, 3 to 6 months, or 6 months to a year. Give you a few more seconds. Okay, I'm going to close this. share your responses. 3% of you said immediately. 3% said 1 to 3 months. 18% said 3 to 6 months. And 77% said 6 months to a year. Okay, thank you very much, everybody, for your responses. And so with nothing further from me, I would like to introduce our speaker, Mr. Adam Platisse. Welcome, Adam.
All right, well, thank you, Robin. And welcome everybody to Sensifar's Microelectronics and Semiconductor webinar. We have close to 300 people that registered for today's webinar all around the world. So good morning and good evening. Thanks for staying up late or getting up early with us today. So as Robin mentioned, my name is Adam Platisse, and I'm the U.S. Sales Manager located in Connecticut, which is in the northeast corner of the U.S. And Alberto Aguirre is our Vice President of Sales. He'll also be joining the webinar for any questions and answers. So we anticipate finishing in less than an hour today, including our questions. And we're excited to showcase the solutions that we have for our microelectronics and semiconductor industries. We've seen a great deal of growth in these two sectors, with the focus mostly being on how we can improve quality in the PCB and semiconductor markets. Previously, I should preface before we move into the agenda, we've seen a lot of, or we've noticed in the past a lot of our customers were using manually focusing their system, where you might have a typical height of 500 microns, where when you get down to a plus or minus 5 micron tolerance, this was achievable with manual. But when you start to get to the 50 micron range, it becomes a challenge to manage the quality assurance or quality control in your production line. So today we'll talk show a lot of our applications that revolve around our automated solutions, from a motorized microscope that automatically does the motorized acquisition to automatically populate that data into our analysis routine, which is called Senso Pro. So in our agenda today, we will talk a little bit about who we are as a company and what our technology is, just to give you a background of Sensifar. And then we'll move into the actual applications, such as our critical dimension measurements, roughness analysis, defect mode and analysis, along with quality control. Finally, before our question and answer, we'll talk about what separates Sensifar and why we're unique in the marketplace. So a little history of the company. Sensifar was founded in 2000. So we have about 50 employees located in our Barcelona home office. And globally, we've sold approximately 1,000 systems. These range in various industries, not only the semiconductor and microelectronics, but also aerospace, automotive, medical device, and all sorts of sciences and universities. Throughout the beginning part of the early part of this millennium, the focus was understanding the markets and developing the technology. It was in 2008 where the shift came to really focus on sales and strategize growth. And by 2014, we had diversified our product portfolio. Today, you will see predominantly our flagship system, the S-Neox, but we do have other systems that range from our sensor heads to other capabilities with our current motorized systems. And then, of course, to where we are today with having a large global footprint in Asia, Europe, and the United States. And ultimately, you can stay tuned for our next webinar to see where we go in the future. So here's a quick snapshot of our partner channels around the world. I, again, am located in the United States in the black dot. and I'm supported with about 4 other partners that help to represent Sensifar throughout North America. And as you can see from the map, we have a large footprint in Europe and Asia as well. This slide illustrates a nice cross-section of our partners and customer references. So plenty of industry and university. And in the United States, we're very proud to have recently partnered with WPI, located in Worcester, Massachusetts. So before we get into the actual applications, I wanted to just talk a little bit about the actual microscope and our technology. This is our latest release. It is our 5th generation 3D optical profiler, the S-Neox. It was released at Photonics West in San Francisco of February of this year. It is the fastest scanning confocal profilometer in the market. It's extremely easy to use, and for those of you that might have known our previous generations, you'll see a few very obvious changes where we've moved to a bridge design for increased stability, and a lot of what else has changed is actually going on in the sensor head, where we improved many of the algorithms to produce the fastest system in the market with no moving pieces. So this allows us to reduce any type of service or any type of extensive calibration that you might see on other systems. The microscope scan head as well is removable. So this will be important to understand later in the presentation, as you can integrate the scan head into any type of automated cell or put on any type of robotic arm or gantry system. It does not necessarily have to be the standalone benchtop system that you see on this slide. So what's inside the scan head? Sensifar has some unique proprietary technology where we are the only company in the world that integrates confocal, an interferometer, and focus variation all into one scan head. And we do have a reflectometer that we can add or not add, depending on how you'd like to have the system set up. Confocal, we do have continuous confocal, which, when I mentioned earlier, were about 5 times faster than any laser-based confocal rastering system. We achieved this with a micro display, which we could talk about later if anyone is interested in further understanding the technology. As far as the interferometer, we offer our coherence light interferometry and phase shifting interferometry. So we are able to achieve sub-nanometer resolution when required. Our latest focus variation is active illumination. So this allows us to handle larger samples, more in the macro or more into the millimeter range of measurements. But what's unique is the texturization capability of our new AI focus variation, where it allows us to achieve almost confocal resolution. And this has been a great step forward for us, and we're very proud to showcase it. So as mentioned earlier, Sensifar has many different types of software programs, but we are going to focus primarily today on our automated solution, and this is called Senso Pro. So with a system, you always have the default freehand capability to draw any of your measurements or ascertain any type of roughness value that you might require. But in order to reduce any type of subjectivity, an engineer can always create an acquisition program which will then automatically be analyzed by our automated Senso Pro program, and that reduces any uncertainty. So this is common when you're measuring large batches, or you have many of the same type of samples where you need to ensure that no parameters have changed in how you're measuring your sample. And then, of course, the data is automatically populated and generated into either a CSV report or any type of custom report that you might want. Okay, so now we will move into the actual measurement capabilities and start seeing what our customers are working on. So this is a sample of a CSP wafer where the customer is actually sawing the different chips from the wafer. In wafer assembly, you have the front end and the back end, where the front end is typically how the wafer is manufactured, and the back end deals with more of the wire bonding and the molding. Sensifar's main strength is in the back end, and this is where you would see here we have a diamond cut, which is actually two separate cuts. The first cut is to separate, and the second cut is to be a smaller measurement to ensure that we're not damaging the chip. So these are dual step heights that could be measured manually, or it can be measured automatically through our SensoPro. Again, because Sensifar has the capability to measure in confocal and interferometry, the user chooses based on what the dimensions of their sample are. So for here, we're looking at roughly about 80 to 100 microns in the X and Y dimension, and we're at about 300 to 400 microns in the Z direction. So for these types of samples, measuring with our confocal capability would be the best choice. On this slide, we see another example that would be better measured with our interferometer. And in this case, we used our PSI, phase shifting interferometry mode. This took about 50 seconds to acquire. On the bottom right, you are able to see the freehand manual measurement, but SensoPro at the top can also automatically identify the critical dimensions and measure the X, Y, Z, center of gravity of where these chips are located in comparison to each other. These chips here, we're looking at about 15 nanometer depth vias. So this would be beyond what we would expect the confocal to measure, and we would utilize our interferometer to handle such types of samples. Radius surface. So this is predominantly seen in MEM industries. Typically with lower powered microscopes, the surface does look flat. So customers have asked us that they have a need to measure what the radius is across the area that look flat. And at the bottom of the image, you can see that there is an actual radius that we are measuring to a specific tolerance. So for CSP backend, tracing is also a very common requirement. For here, the tracing is roughly 3 to 4 microns in linear dimension, with about 1 to 2 microns in spacing. So to measure these 3 micron spaces, we were able to achieve a 0.5% repeatability error. You can also choose if you'd like to image these types of samples with the confocal capability, which does provide the best lateral resolution, or you could also image it with our interferometer, so you can have very tight tolerance and high resolution in the Z range. Both capabilities work. So now we'll move on to roughness measurement. In this type of sample, what we're looking at on the PCB board is copper roughness. This is a typical control for understanding the adhesion and how rough or how smooth the adhesion would be. So we're able to, of course, as mentioned prior, you can always manually achieve these measurements, but we can also program in, for example, the SA, the SQ, the SZ, or SP values for SensoPro to automatically provide that data for you. Some people, as you mentioned, as we saw in the poll earlier, you might be using a stylus. Of course, a stylus is destructive, so understanding what the RA value, understanding what the SA value is, will give you a lot more information about the surface roughness in the field of view. And we do have the ability to correlate back to a SA to RA value. That is within the capability of the system if any of your current requirements need that roughness value. Here's an image of a CMP application for chemical mechanical processing. And on the right side of the screen, you see one of our older systems. This is a previous generation where we've integrated it into the actual CMP machine. So what is important in putting the system to be able to measure the pad in real life time is that we're able to understand the current capability or where the pad is in its life cycle. So oftentimes vendors will mention that sell the pads that you get about 8 hours out of the pad. But we've been able to measure it in real time where we can extend the pad's life up to 28 to 30 hours. So this is a nice cost savings function by better understanding what the pad's surface is. And we achieve this by using a 100x water objective, or a 20x as well, is what you see in this image. Here's a quick example of a confocal Z-stacked image of the used compared to the new pad. For photovoltaics or solar cells, again, understanding what the real 3D surface area is what allows us to understand the efficiency of the solar cell. SDR is an ISO 25178 parameter that allows us to understand how much surface area is actually collecting light. So this could be kind of understood if you were to think of for those of you that know the state of Vermont, it's very mountainous. And if you were to compress all those mountains down, it would expand out the area to be more or less probably close to the size of Texas. So by understanding all the different surface areas that might be in a vertical orientation on your sample, you can determine what the efficiency is, where the higher the percentage, the more area could collect information from. For defect mode analysis, what we're looking at here is a bond pad defect. These are probe depths where it is important to understand how close that impression came to the underlying chips. Now, we see this commonly in, for example, the cell phone industry, where if the impression is too close, it could cause a failure. That typical answer that we hear from those customers, well, the solution is you buy a new phone. However, we also have such chips in the automotive industry where it could be the difference of your car stopping or not stopping. So it is important to ensure that these chips do not fail. And we can measure this with a single field of view relatively quickly using our interferometer. And we can determine the depth of the bond pad, the bond pad impression. Another similar application is after the wire bonding. What's important here is force. Understanding that force would help us to learn if the force was too weak, there's potential for the bond to separate. But if it's too strong, it could create cracks or damage the underlying layers. And on the left image, you see the dark impressions where we can measure how deep those impressions are to determine how close they came to the underlying layers. So what's unique about Sensifar is we do have the capability to measure such an image with a 10x interferometer lens. Or we do come across competitors that don't offer that capability. And in order to get this resolution, they would need to use a 50x or 100x to measure the same field of view in confocal. So what that requires them to do is stitch together multiple X and Y images. So you end up creating a mosaic, which is time consuming and also does not have the vertical resolution that an interferometer provides. So quality control. We're just going to show you a little movie here. And we'll let that run, where you can automatically have the microscope recognize where the fiducial markings are on your sample, and then move to the actual samples for measurement. Everything that is being acquired here can move to a pass-fail CSV reporting file, where you can then go back to the actual sample and discover if it was within or outside of your predetermined tolerance. This movie's not too long. We'll just let it continue to measure as it shows you how it does the autofocus on each position and does the acquisition. So that was our interferometer doing 828 images in Z. It's a fairly quick acquisition for such a for so many images. And those little lines that you see are the interferometer band interference bands moving across the screen. So on the bottom right, it details that we are doing the analysis now, and it automatically generates your Excel report, where you can find which parts of your sample passed, and again, which parts failed. And this can also be programmed into any type of data management routine that you might have at your lab. So another capability that we have is understanding warpage. We achieve this through our coordinate function routine. Here, we don't necessarily need to measure the entire wafer, though we can handle wafers 6 inches or larger. But we can measure 21 predetermined points, which take about, for this example, was about 2 minutes and 45 seconds. We can achieve that with a 20x with our confocal capability, and it doesn't require any stitching, but still gives us 0.5 micron or 500 nanometer resolution, which is enough to understand the warpage or the bow of your wafer. Gas wafer, what's commonly looking to be understood is the amount of vias and the dimensions of the vias. You can manually measure them, of course, but with SensoPro, we do have the automated plugin that allows us to automatically look for what the bottom or the top diameters are, the height, and again, the relative XY position to each other. One thing to mention is that if you do have custom needs, Sensifar welcomes the opportunity to work with you to develop a unique analysis program that could be added as an additional plugin to SensoPro. Roundness of the via is also a critical dimension, where there's multiple ways that we can measure it, of course, in X and Y and Z, but also understand how the roundness propagates as it moves through the Z dimension. And we can see that with the laser holes, such as on the right side of the top part, where the top and bottom center are distributed, or where the actual X hole position would be. Traces are another important aspect in the market. Similar to what you've seen before, we can assign a specific location or a coordinate location through a number sequence, so you can move to the individual trace, or you can average them all to understand what the standard deviation would be. All the parameters that you see at the bottom are freely configurable. If you require them, we can add more, or we can always delete them. They can be set to whatever your requirements are. Trenches, same idea, and some of you might think that we've used maybe a graphics company to create some of these images, but these are all actually images taken from the SNEOCs. So on the left side, you see the manual measurements, similar to what this looks like. It's from Senso Pro, or I'm sorry, from Senso Map. And I should mention that Senso Map is the licensed version of Digital Surf's Mountains. So we have the complete capability to fully analyze your sample either manually or using what's on the right side, our Senso Pro plugin, to give you the measurements automatically. Step height is another crucial measurement requirement, and you have the ability to measure them independently or across the entire area, and you can average them together. These are done through thresholding techniques, which can be provided to the user, or they can be locked in so no changes are acquired. And so this would be useful for someone that has a multi-user lab where they are not looking for any of the parameters to be changed. The engineer that creates the routine would be the only individual that would have control over any potential change. Wafer processing. This is taken in our Senso Scan and Senso View software, so it's very it's freehand, where the user can draw the profile wherever they see fit. They can apply any type of form removal or ISO parameter as well. But what's important here is understanding the average depth. So we can find the lowest depth or the highest depth with the profile at the bottom, but we can also expand the profile to cover the entire serial number and understand what the average depth is across those laser markings. Here's another example of what Sensifar's general reporting analysis would look like. So all the metadata, all the information of how the sample was acquired, and any of the annotations are automatically saved in a visualization report, which you see on the left. We can customize this, but it does create everything from when the acquisition happened to what the quantitative and qualitative information look like. Wafer processing as well, again, another easy capability to understand the average step height, where you can choose which plugin you'd like to use. And again, Sensifar does welcome the opportunity if you have custom needs. We are flexible where we're able to take on such challenges and provide you those types of solutions. Bump height, diameter, and coplanarity are mostly what's used, where we'll threshold out where the bumps are, and we can understand what critical information is required for each one of them. What you see here is how we can essentially assign an ID to each one of the threshold points. So you can go back to this at a layer point and rediscover what might have been in or outside of tolerance for QA and QC needs. So a little bit of, you might be seeing the same thing for a lot of these types of samples, but it's a very powerful software where, again, on the top right of the Senso Pro screen, you can see where, depending on what your sample is, it would, this is where the user would choose which plugin to use. And pretty close to the end here, this is one of our integrated solutions, where our microscope scan head is actually inside the system that you see here, automatically in live time, generating the reports and utilizing through SDK all the analysis routines that you have seen throughout the presentation. So ultimately, again, why Sensifar? What's unique about our capabilities? For one, we are the fastest scanning confocal microscope in the market. So this, of course, allows you to save time and money in any of the work, analysis, or research that you're doing. We're also the most versatile scanning profiler in the market, as we're the only company in the world to offer confocal, interferometer, and focus variation all in one scan head. And we also have the reflectometer, which can be added if required for thin film measurements. Senso Pro, which is what we predominantly were looking at today, offers a fully automated solution for the QC market. In default settings, you always have the ability to do your own freehand measurements, but Senso Pro is the tool that many of our customers use in the microelectronics and semiconductor industries for eliminating any subjectivity in their analysis routines. And we've been in business, well, geez, a little bit over 18 years now. So we have plenty of experience to, again, take on custom challenges and provide any solution that you might be looking for, either in R&D or QA/QC. Well, again, we just want to thank everyone for joining us today. We hope it was somewhat informative, and maybe you gleaned a little bit of a new perspective about the work that we're doing in the semiconductor, PCB, microelectronics world. And with that, we'd like to open up the webinar to answer any questions that you might have, or receive any feedback as well. So thank you again, and I think Robin will be joining us now.
Thank you very much, Adam, for that presentation. And attendees, if you have any questions, now is the time to enter them into the questions box. And we do have a couple of questions here, Adam. I'll begin with the first question. What is active illumination?
Okay, so active illumination is our new AI focus variation algorithm. It's where we actually texturize the surface. And what this allows us to do is achieve much higher resolution and focus variation. Focus variation is your traditional bright field microscope, where you're basically collecting all the information, and then it's up for the detector to determine which pixels were in or out of focus. This is standard in all across all microscope vendor or microscope manufacturers. But what our next step algorithm does with the AI capability is it actually texturizes the surface. So it allows us to get the pixels just a little bit more in focus, where we can increase the resolution to just below where confocal takes over.
Okay, thank you. And our next question here. How should I decide in which technology to measure the roughness?
So it's a good question, and it depends on what your roughness tolerance is. Of course, ISO has many different levels that you might need to achieve, but what we found is typically using the interferometer, especially for single nanometer roughness, it would be the most appropriate for measuring roughness or surface finish at such small detailed levels. So it really comes down to being sample dependent and what parameters you're looking to acquire. And of course, we can help you with that. This is something that we typically do through a proof of concept or demonstration, where we'll run the different routines, and we can show you the difference of the quality quantitatively and quantitatively of what the different methods or imaging modes would produce.
Thank you, Adam. There was a little bit of an audio issue there, and I apologize to the attendees. I hope everybody was able to hear Adam. I don't hear the audio issue again right now. So I'm just going to move on to this next question here. I am currently using S-Link's optical profilometer. Could you please let me know how to choose the best cutoff value while using ISO filter to determine surface roughness?
Well, for that, I might ask our other partner, my manager, Albert, see if he can provide some insight to what the customer might be working with.
Okay, that's great. Adam, your sound is breaking up. I don't know if you can hear me well, but Alberto, would you care to respond to that question?
Yeah, thank you, Robin. This is Alberto. Since Adam is having some issues, I will try to cover him. So, related roughness measurement, it's always depending on the kind of roughness, the nominal value that you want to measure. But in an optical profiler, we find a good compromise to use a 50x lens with a cutoff of 80 microns. This is very standard for this kind of applications. Let's say that if you use a 10x lens, probably spatial sampling is not good enough. It is too short. But also, if you use a 150 focal, probably the field of view of the region of interest is too small, and it's not reliable. So 50x is a very good compromise for this.
Okay, thank you very much. So I'm going to try another question here and see how the audio is. Alberto, you sounded okay to me. Okay, so question is, how do you choose which imaging mode to use? For example, does the system automatically scan in confocal / interferometry and focus variation, or does the user select which imaging mode to use based on their application?
Okay, Robin, if you can hear me okay, I can answer that.
But
You know,
Adam,
I'm having
okay.
a little bit of trouble, Adam. I'm sorry about that.
All right.
Okay. So, yeah, yeah, this is a typical question for our system. As Adam said, our optical profilometer is combining 3 technologies in the same head. So we need to decide, we need to choose one of these. So when we talk about surface finish, either interferometry or confocal are very good options. Let's see, focus variation, we use it more for measuring shape. So then the question is how we choose between confocal and interferometry. The answer is the following. If you can use interferometry, go for it, because you have the system noise of the vertical resolution is always 1 nanometer, regardless the objective. Okay. But in some cases, interferometry is not good enough because the local slopes are too high. So in those cases, I would prefer to use a confocal mode. So let's say that interferometry is better with a vertical resolution, confocal is better for the lateral resolution. But at the end, if you can use interferometry, and if you have a limitation on lateral or high slope, then we use confocal.
Okay, thank you, Alberto. So the next question here is, how do you achieve 5 times faster scanning speed when compared to a laser confocal system?
All right. Yes, this is because of the way we do how we take a confocal image. According to the ISO 25178, there are three kinds of aerial confocal microscopes. The first kind is a laser scanning confocal. The second one is a spinning disc, and the last one is our technique, which is using a micro display. So the way we do the confocal, the confocal rasting is with a micro display. So we don't have moving parts inside the head. So that means that we can do it much faster. So we don't have to go point by point. We can cover a large area in a much short of time. Not only that, is that we cannot be, so the fact that we can do the confocal rasting much faster, it allows us to move in continuous mode to do the axial scanning in continuous mode. So we don't need to stop. We don't need to do steps. That makes a big difference with a laser scanning confocal.
Okay, thank you very much, Alberto. Next question here. What is the smallest resolution you can achieve with the system?
if we talk about vertical resolution, with a phase shifting interferometry technique, we can get to 0.01 nanometer. And if we talk about lateral resolution, with a 150x confocal lens, we can go to the diffraction limit to 300 nanometers. So we can measure a grating of 300 nanometer pitch.
Okay, thank you very much. Next question here. When measuring step heights in the range of 10 to 100 nanometer, which interferometry mode would you use? PSI/ePSI/VSI?
Yep. So, well, the system is including the three technologies, interferometry. PSI, as I told you, is the best one in terms of vertical resolution. You can get this 0.01 nanometers, but you have the limitation that you cannot measure a step height larger than lambda quarter. So if we are using a blue LED, that means that the limitation is 120. So if we have a step height smaller than 120 nanometer, I will use PSI.
Okay, thank you. We have one more question here, and I'm in the meantime, attendees, if you have questions, please do enter them in. We still have some time to respond to them. The last question I have right now is the system modular for future upgrades, and do you offer any demonstration units for immediate or cost-effective delivery?
Yes, we do. In fact, these two questions, but so we have right now we are presenting now the newest Neox. This is the 5th generation. So right now we have available our former S Neox 4th generation demo units. And which was the first part? Sorry, Robin, can you repeat that?
Oh, sure, I can repeat it. Is the system modular for future upgrades?
Oh, yes. So you can get a basic S Neox, including the three technologies with the bridge and a manual stage. Okay. Afterward, you can buy different options like the motorized stage. We have option from 4 to 3 inches up to 12 by 12 inches. It can be upgradable to a PSO. It can be upgradable with a Sensor Pro software. You can buy more lenses. So it's normal that our customers start with a basic configuration, and every year they expand and they extend their configuration.
Okay, thank you very, very much, Adam and Alberto. And attendees, if you have questions for either Adam or Alberto, Adam's email address is here on the screen. Please do not hesitate to contact him. And at this time, I'm going to close the webinar, and a recording of the webinar will be available shortly. All attendees and registrants will receive a link to the recording tomorrow in a follow-up note. I would like to thank our presenter, Adam Plantis and Alberto, and Sensifar Metrology, and all of you for participating in today's webinar on optical metrology solutions from Sensifar, hosted by Photonics Media.
Thank you, Robin.
Thank you, everybody.
Thank you. Have a nice day.